In this video, we are going to discuss the formation of cyclic acetals. Specifically, we can react an aldehyde or ketone with a 1,2 diol and catalytic acid, and we can generate a 5-membered ring cyclic acetal, or we can use a 1,3 diol and generate a 6-membered ring cyclic acetal. Now, tracking with you, if we were to just have to predict the product of this reaction here, what you could do is draw your structure without the C double bond O. Then imagine that each of the oxygen atoms of your 1,2 diol will connect to the former carbonyl carbon. And if it's a 1,2 diol, there's 2 carbons connecting the 2 oxygen atoms. If we instead were to react with our 1,3 diol, you could draw your structure without the C double bond O. Bond the carbon to your oxygen atoms of your 1,3 diol, and then connect those via a 3-carbon chain. The 1,2 diol makes the 5-membered ring, the 1,3 diol makes the 6-membered ring, and they would be generated via the exact same mechanism. Okay, so what we're going to do here is look at the mechanism for forming that cyclic acetal. We're specifically going to form the 5-membered ring cyclic acetal by reacting with our 1,2 diol and catalytic acid. Mechanistically, we are going to protonate the carbonyl oxygen first. Got to protonate to make it more reactive. Then your 1,2 diol will attack and bond. Okay. We then need to deprotonate the oxygen atom that just attacked and added in. That would then form the hemiacetal intermediate. We now have an OH group and an OR group bonded to the same carbon. And ultimately, to form the acetal and to cyclize, we need to kick out a water-leaving group. So in this step here, let's protonate the OH component to create our water-leaving group. From there, we are going to collapse our lone pair from our neutral OR component and form a pi bond, and that will then expel a water-leaving group. Now, as we form that carbonyl, instead of another alcohol intermolecularly attacking, what's going to happen in this step is an intramolecular attack. The alcohol within the chain here will attack intramolecularly, and that's going to generate a 1, 2, 3, 4, 5-membered ring. Tracking with you, that's 1, 2, 3, 4, and 5. So we see an intramolecular attack here. Alcohol within the chain attacks and bonds, and we have enough reactivity because the carbonyl is charged positive. And finally, we are going to deprotonate the oxygen atom, making that into our neutral acetal structure. Okay. Now, this mechanism is identical to the one that we just covered on the other page, where we formed a normal acetal. It's just that if you use a regular old alcohol, then we had an intermolecular attack when the second alcohol incorporated. But if you're using a 1,2 diol or a 1,3 diol, after we kick out the water-leaving group, it will be that other alcohol within the chain that will attack intramolecularly to generate a ring. And if we started off with our 1,2 diol, we're going to form our 5-membered ring, cyclic acetal. If we instead used a 1,3 diol, we'd form a 6-membered ring, cyclic acetal. All right, let's recap that mechanism one more time. We need to protonate first to increase the reactivity of the carbonyl carbon. Our 1,2 diol will then attack and bond. We need to deprotonate the oxygen atom to stabilize its linkage in the structure and form our hemiacetal intermediate. From the hemiacetal intermediate, we need to conceptualize it protonating the OH component to create a water-leaving group. And then we'll expel that water-leaving group by collapsing a lone pair from the neutral OR portion. That creates our charged carbonyl intermediate, and the alcohol within the chain will then attack intramolecularly, forming a 5-membered ring. The oxygen that just attacked at that point is charged positively. We are then going to deprotonate that oxygen atom to form our cyclic acetal group. Okay? Wherein we said both of the oxygens have result attached to what was the carbonyl carbon, and those oxygens are connected via that 2-carbon chain. So let's imagine we just show another example. Perhaps we have this structure here. If I were to react with my 1,2 diol and catalytic acid, I'm going to imagine drawing my structure without the C double bond O. I'll then connect each of my oxygens from my 1,2 diol to that carbon and connect them via 2-carbon chain. Now watch this. Let's say that we instead have this example here. Okay, let's say we have this structure and we react possibly with acetone, and we do so with an acid catalyst. What feels different about this and is different is in our reaction expression, the carbonyl is over the arrow, and our 1,2 diol is before the arrow, whereas up here the 1,2 diol was over the arrow, and the carbonyl was to the left of the arrow. I'm going to use the same strategy, essentially, to predict my product here. What I'm going to do is imagine connecting each of those oxygen atoms to the former carbonyl carbon, which is that carbon there. I connect each of my oxygen atoms to that carbon, former carbonyl carbon, and that former carbonyl carbon had 2 methyl groups. So off that carbon, I will have 2 methyl groups. I think that's the easiest way to visualize this in both strategies. Coming back to the first one here, I imagined getting rid of the carbonyl, and I connected each of my oxygen atoms to that carbonyl carbon, and then there was a 2-carbon chain separating them. Here, because that's the larger portion visually, I might start by drawing that, and then I'm going to imagine each of those oxygen atoms are going to connect to the former carbonyl carbon, and that former carbonyl carbon has 2 methyl groups attached to it, and that would be the structure of the acetal that I generate. Okay? Now, ultimately, acetal formation can be reversible, and we'll talk about this in the next video, but just as a little bit of a teaser, you could have an acetal, and you could then react with water and acid, and reacting with water and acid would reform the carbonyl from which that was derived, and you would then sever the connections that each of those oxygen atoms have to the carbon, and we would regenerate the 1,2 diol and a carbonyl. Okay, acetals can form, but then we can hydrolyze that acetal with water and acid, and that will be the topic of our next video.